Hello there, and welcome to Fall Asleep. Tonight, we are going to spend time with something that is out there right now. Not in a laboratory, not in a museum, not in any building on Earth. It is 1.5 million kilometers away, in a place called the second Lagrange point. It sits there in the dark, alone, perfectly balanced between the gravitational pull of the Earth and the Sun. It never moves toward us. It never drifts away. It simply holds its position, orbiting the Sun in step with the Earth, a quiet companion at an extraordinary distance. This is the James Webb Space Telescope, and tonight, we are going to sit with it for a while. We are going to think about how it got there, why it is where it is, what it sees from that remote position, and what it means to have placed something so precise, so fragile, and so magnificent that far from home. The James Webb Space Telescope is the largest and most powerful space telescope ever built. Its primary mirror is 6.5 meters across. It is made of 18 gold-coated hexagonal segments that unfolded in space like the petals of a flower. It is designed to see infrared light that the human eye cannot detect, light that carries information from the most distant and ancient parts of the universe, galaxies that formed when the cosmos was less than 1 billion years old, the first stars, the chemical fingerprints of distant atmospheres, all of it collected by a mirror floating alone in the dark, 1.5 million kilometers from home. Before we travel out to visit it together, if you find these journeys restful, I invite you to like, subscribe, or leave a gentle thought below. It helps other tired minds find their way here, one sleepy soul at a time. But for now, there is nothing you need to do. Let your jaw unclench. Let your shoulders drop. Let your breathing slow into something easy, like the breathing of someone who has already let the day go. And as your mind begins to gently release the weight of today, join me as we travel outward, away from the familiar, to the quiet place where the Webb telescope waits. Let us begin. The Webb telescope represents the work of more than 10,000 scientists, engineers, and technicians across 20 countries over more than 2 decades. Planning for it began in the mid-1990s, when the Hubble Space Telescope had been in orbit for just a few years. It was proposed as the next great observatory. And it took almost 30 years from that first proposal to the first scientific images. The cost was approximately $10 billion. The delays were many. The technical challenges were extraordinary, but the telescope that finally launched in December 2021 exceeded expectations in almost every measurable way. Its mirror alignment was better than required. Its orbit required less fuel than budgeted. Its instruments are performing beyond their design specifications, and the science it is producing is already reshaping our understanding of the early universe, of star formation, and of planetary atmospheres around distant stars. To understand why the Webb telescope is where it is, we need to understand the Lagrange points. They are named after the 18th century Italian-French mathematician Joseph Louis Lagrange. In 1772, Lagrange was working on a mathematical problem that had occupied astronomers for decades. The three-body problem. If you have two massive bodies, like the Earth and the Sun, orbiting each other, and you add a third much smaller body, where can that third body be positioned so that it stays in a fixed position relative to the other two? The full three-body problem has no general solution. It is one of the great unsolvable problems in classical mechanics. But Lagrange found 5 special solutions, 5 specific points in space where the gravitational forces of the two large bodies and the centrifugal force of the rotating system balance each other perfectly. He called them equilibrium points. We call them Lagrange points, labeled L1 through L5. The first Lagrange point, L1, sits between the Earth and the Sun, about 1.5 million kilometers from Earth in the direction of the Sun. L2 sits on the opposite side of the Earth from the Sun, also about 1.5 million kilometers away, but pointing away from the Sun into the outer dark. L3 sits on the far side of the Sun from Earth. L4 and L5 sit in Earth's orbit, 60 degrees ahead and behind the Earth. L2 is where the Webb telescope lives, and the choice of L2 was not arbitrary. It is the most useful position imaginable for the kind of science the Webb telescope is designed to do. The Lagrange points L4 and L5 are different in character from L1, L2, and L3. L4 and L5 are stable equilibrium points. An object placed at L4 or L5 and given a small push will oscillate around the equilibrium point rather than drifting away. This is why L4 and L5 are occupied by real populations of asteroids. The Trojan asteroids of Jupiter are concentrated at Jupiter's L4 and L5 points, thousands of them, orbiting the Sun in the same orbit as Jupiter, but 60 degrees ahead and behind. Earth also has Trojan asteroids at its L4 and L5 points, though far fewer than Jupiter. The stability of L4 and L5 means that objects can accumulate there over billions of years. The instability of L2 means that the Webb telescope must actively maintain its position with small thruster firings. But L2 is still far more useful for the telescope's purposes than any stable point would be. The choice of L2 over L1 or L3 was straightforward. L1, between Earth and Sun, would expose the telescope to solar heating from the front. L3, on the far side of the Sun, is too far away, and the Sun would block communications. 2 is the Goldilocks position for a cold infrared telescope, far enough from Earth to avoid its heat, close enough for regular communication, always in the right geometric relationship to the Sun for the Sunshield to work. Why is L2 so special for astronomy? The answer comes down to two things: stability and temperature. At L2, the Webb telescope orbits the Sun at the same rate as the Earth. It takes 1 year to complete one orbit. This means that the Earth always stays in approximately the same direction, about 1.5 million kilometers away. And more importantly, the Sun always stays in approximately the same direction too, always behind the Earth from the telescope's perspective. This has a critical consequence. The Webb telescope can deploy a sunshield, a large layered barrier positioned between the telescope and the Sun, the Earth, and the Moon simultaneously. The sunshield is roughly the size of a tennis court. It is made of 5 thin layers of a material called capton, coated with aluminum and in some layers silicon. Each layer reflects sunlight and radiates heat away into space. Together, the 5 layers reduce the temperature on the cold side of the shield by an extraordinary amount. The sun-facing side of the sunshield reaches temperatures of about 85 degrees Celsius. The cold side, where the telescope's mirrors and detectors sit, drops to around -233 degrees Celsius, just 40 degrees above absolute zero. The telescope needs to be this cold because it observes infrared light, and anything warm emits infrared radiation. If the telescope itself were warm, it would glow in the infrared and blind its own detectors. By keeping the telescope at near absolute zero temperatures, behind the sunshield at L2, the Webb can see the faintest infrared signals from the most distant galaxies without any interference from its own heat. The temperature requirements for the Webb telescope are so extreme that the engineering to achieve them is a significant part of the telescope's story. At -233 degrees Celsius, the detectors of the near-infrared instruments work by passive cooling alone. The sunshield removes enough heat that the telescope's cold side simply radiates heat into the universe and cools naturally. But MIRI, the mid-infrared instrument, requires even lower temperatures, below -266 degrees Celsius. just 7 degrees above absolute zero. Passive cooling cannot achieve this. MIRI uses a mechanical cryocooler, essentially a refrigerator, that actively removes heat from the instrument. The cryocooler was a significant engineering challenge. It has to work reliably for years in the vacuum and cold of space, with no maintenance, driving temperatures down to levels that are among the coldest anywhere in the solar system. At the distance of L2 from the Sun, the natural background temperature of space is about -270 degrees. MIRI's operating temperature is warmer than that background only because the telescope itself, even with the Sunshield, generates some heat. The 5 layers of the Sunshield are not in contact with each other. There are gaps between each layer. This is intentional. The gaps allow heat to radiate sideways out of the shield rather than accumulating between layers. Each layer is slightly larger than the one above it on the cold side. This staggered design ensures that sunlight does not sneak around the edges of a smaller layer onto a larger one below. The engineering of the Sunshield is a masterpiece of thermal design. Every surface, every angle, every gap has been calculated to maximize the temperature drop from sun-facing side to cold side. The journey to L2 was one of the most complex and nerve-wracking sequences of events in the history of space exploration. The James Webb Space Telescope launched on December 25, 2021, from the Guiana Space Center in Kourou, French Guiana. It launched aboard an Ariane 5 rocket, one of the most reliable heavy-lift rockets ever built. The launch itself was nearly perfect. The trajectory was so accurate that the telescope required far less fuel than planned for its journey to L2. This extra fuel will extend the mission lifetime beyond the planned 10 years. The Webb telescope spent approximately 30 days traveling from Earth to L2. During that journey, it performed what engineers called the 29 days on the edge, because the telescope had to unfold itself in space. There was no way to test the full unfolding process on Earth. The telescope is too large to fit inside any building in its deployed configuration. So engineers designed a system of 144 individual mechanisms that had to work in sequence. If any single one of them failed, the mission would be lost. The Sunshield unfolded first. Its 5 layers stretched out across the telescope structure in a choreographed sequence over several days. Then the secondary mirror, the small mirror positioned in front of the primary mirror, deployed on its 3-legged support structure. Then, one by one, the 18 primary mirror segments unfolded from their stowed position and locked into place. Each hexagonal segment was then adjusted to nanometer precision using tiny actuators behind each mirror. All of this happened while the telescope was between Earth and L2, in the cold dark of space, controlled by a team at the Space Telescope Science Institute in Baltimore, Maryland, who could only watch and wait for signals to confirm each step. The Sunshield deployment was the most complex and anxiety-inducing part of the entire process. The Sunshield is made of 5 layers of Kapton membrane. Each layer is very thin, about as thick as a human hair. The total area of all 5 layers combined is about the size of a tennis court. When folded for launch, the Sunshield occupied a compact volume inside the Ariane 5 rocket fairing. Unfolding it required dozens of precisely sequenced steps, latches released, membranes pulled taut by motor-driven cables, the 5 layers separated from each other to provide insulating gaps between them. Each gap contributes to the temperature reduction across the shield. Engineers at Northrop Grumman, which built the Sunshield, had tested the deployment mechanism thousands of times on Earth. But on Earth, you cannot simulate the combination of vacuum, cold, and zero gravity that the Sunshield would experience in space. The engineers knew their tests were imperfect simulations. They had modeled and analyzed every possible failure mode. They had introduced redundancy wherever possible. But they also knew that some uncertainty remained. When the Sunshield finally deployed fully and correctly in space, the relief among the engineering team was palpable. The primary mirror of the James Webb Space Telescope is made of beryllium. Each of the 18 hexagonal segments is machined from beryllium and then coated with a thin layer of gold. Gold is used because it is an excellent reflector of infrared light, better than aluminum or silver in the infrared wavelengths that the Webb is designed to observe. The gold coating is extremely thin, about 100 nanometers, 100 billionths of a meter. The total mass of gold on the entire primary mirror is less than 50 grams, enough to coat a fingernail to a significant thickness, spread across 6.5 meters of mirror surface. Beryllium was chosen for the mirror substrate because it is exceptionally stiff and light. It holds its shape extremely well at cryogenic temperatures. Most materials contract or distort when cooled to near absolute zero. Beryllium barely changes. This dimensional stability is critical. The 18 mirror segments must together form a surface accurate to within a fraction of the wavelength of the infrared light they are collecting. That means the surface must be smooth and precisely curved to within tens of nanometers, tens of billionths of a meter, across a mirror 6.5 meters wide. The alignment of the 18 segments was one of the great engineering challenges of the mission. After the telescope arrived at L2 and cooled down, engineers spent several months carefully adjusting each segment. They observed a single bright star and looked at how the 18 separate images of it could be combined into one perfect image. Slowly, segment by segment, adjustment by adjustment, the mirror was aligned. When the first full-resolution test image was released in early 2022, the sharpness and detail surpassed even optimistic expectations. The alignment of the 18 mirror segments was performed using a technique called wavefront sensing and control. Astronomers pointed the telescope at a single bright star and observed how the light from that star was being focused by the mirror. Each of the 18 segments, being slightly misaligned after deployment, produced its own slightly displaced image of the star. Early in the alignment process, a single image of a star looked like a field of 18 separate dots. Engineers could identify which dot came from which segment based on the known geometry of the mirror. They then commanded the actuators behind each segment to adjust its position. After several rounds of adjustment, the 18 images merged into one. Then came fine alignment, adjusting the shape of each segment individually to correct for small surface errors. The final aligned image of a star showed diffraction spikes of extraordinary sharpness. The segments were aligned to within a fraction of the wavelength of infrared light, better than 50 nanometers of accuracy across the entire 6.5 meter mirror surface. It was one of the finest optical alignment achievements in the history of astronomical instrumentation. You are lying very still now. The day has grown distant. The thoughts that pressed close earlier, the plans, the small worries, the things left unfinished, have begun to thin and soften. Your breathing has found its own pace, slow, easy, unhurried. And as you rest here, I want you to imagine traveling outward, not on a rocket, not with any speed that would be uncomfortable, just drifting, slowly, away from the planet, away from the cities and the oceans and the atmosphere, into the dark above. The earth falls behind you. First, it is enormous. Then it is large. Then it is a sphere the size of a marble. Then it is simply a bright blue point of light in the dark. And 1.5 million kilometers from that blue point, something floats in silence. You can see it from here. A gold hexagonal mirror, 18 segments arranged in a honeycomb, catching the faint light from a billion galaxies. A 5-layer sunshield stretched out like a kite, one side facing the sun and the earth, one side facing the deep universe. Cold on the dark side, almost as cold as space itself, and perfectly still. It does not vibrate. The onboard systems that might cause vibration are dampened carefully. The telescope watches the universe with a steadiness that no ground-based telescope can match. No wind, no atmosphere, no thermal shimmer, just the gold mirror, and the deep dark, and the light arriving from the beginning of time. You are here with it now, 1.5 million kilometers from Earth. In the quiet, in the cold, in the extraordinary patience of a machine built by thousands of people to look back to the very beginning of things. The Webb telescope does not rotate to point at different parts of the sky. Instead, the entire spacecraft rotates. The telescope, the Sunshield, the bus that carries the power and communication systems, all rotate together as a rigid unit. This places a constraint on what the telescope can observe. At any given time, the telescope can only look in directions that keep the Sunshield between it and the Sun, Earth, and Moon. This defines an allowed viewing zone, a large band of sky that moves through the year as the Earth orbits the Sun. Most of the sky is accessible at some point during the year. But the ecliptic plane, the plane of the solar system, is accessible only for limited periods, and the very poles of the ecliptic, directly above and below the solar system plane, are accessible continuously. This makes the ecliptic poles particularly valuable for deep field observations, where the telescope needs to stare at the same patch of sky for many hours. The Webb deep fields are located near the ecliptic poles, where the telescope can observe without interruption. The L2 orbit is not perfectly stable. This is a feature of all the Lagrange points except L4 and L5. At L2, the equilibrium is what mathematicians call unstable, like a ball balanced on top of a hill. If the ball is perfectly balanced, it stays, but any small perturbation, any tiny push in any direction, causes the ball to roll away from the top. The Webb telescope would drift away from L2 if left alone. To counteract this, the telescope carries a small amount of propellant and performs occasional station-keeping burns, small thruster firings, calculated carefully, that nudge the telescope back toward its nominal orbit. These burns are infrequent, perhaps a few times per year, and they consume only a small amount of fuel each time. The telescope does not orbit L2 itself. It orbits around L2 in a large halo orbit, a path that takes it in a wide loop around the L2 point rather than sitting exactly at it. This halo orbit keeps the telescope out of the shadow of the Earth, which would cut off sunlight to the solar panels that power it, and it keeps the telescope in a good position for communicating with Earth. The telescope communicates with Earth through the Deep Space Network, a system of large radio antennas located in California, Spain, and Australia. Because these antennas are spread around the world, at least one of them can always see the telescope regardless of the Earth's rotation. Data from the Webb's observations are transmitted to Earth and received by these antennas, then sent to the Space Telescope Science Institute, where scientists around the world can access them. The data that the Webb telescope produces is transmitted to Earth twice per day during communication passes with the Deep Space Network. Each pass lasts a few hours. During that time, the telescope transmits its stored observations at a rate of about 28 gigabits per day total. The data arrives at the Space Telescope Science Institute in Baltimore, where it is calibrated, processed, and distributed to scientists. The Institute manages the telescope's observing schedule, responding to proposals from astronomers around the world who apply for observing time. Time on Webb is precious and competitive. The telescope receives far more proposals than it can accommodate. Each proposal is reviewed by panels of expert astronomers who assess its scientific merit and feasibility. The selected proposals are scheduled efficiently, minimizing the time spent moving the telescope between different targets. Observations that require the same general pointing direction are often grouped together to reduce overhead. The result is an observing schedule that is dense, efficient, and constantly evolving as new discoveries prompt new observations. The Deep Space Network antennas are enormous. The largest are 70 meters in diameter. They have to be, to receive the faint radio signals from a telescope 1.5 million kilometers away. The signal that arrives at Earth from Webb is extremely weak. It has spread out over a sphere 1.5 million kilometers in radius by the time it reaches our antennas. But the antennas are sensitive enough to receive it reliably. 2 communication passes per day are sufficient to download all the science data the telescope produces. The instruments aboard the James Webb Space Telescope are among the most sophisticated ever placed in space. There are 4 main science instruments: the near-infrared camera, known as NIRCam; the near-infrared spectrograph, known as NIRSpec; the mid-infrared instrument, known as MIRI; and the near-infrared imager and slitless spectrograph, known as NIRS. NIRCam is the primary imaging camera. It captures images in near-infrared light from wavelengths of about 0.6 to 5 microns. It was built by the University of Arizona. NIRSpec can observe up to 100 objects simultaneously. It takes spectra, breaking the light from each object into its component wavelengths. Each spectrum reveals the chemical composition of the emitting object, its temperature, its velocity, its distance. NIRSpec was built by the European Space Agency and can observe 100 galaxies or stars at once by using a programmable array of tiny shutters. Each shutter is smaller than a grain of sand. The array contains 250,000 of them. Scientists can program which shutters to open for any given observation. MIRI observes at longer mid-infrared wavelengths, from 5 to 28 microns. It requires the coldest operating temperature of any Webb instrument, below 7 degrees above absolute zero. MIRI is cooled by a dedicated mechanical cryocooler as well as by passive radiation into space. It can image star-forming regions, dust-obscured galaxies, and the thermal emission from planets and their atmospheres. Together, these 4 instruments give the Webb an observing range that covers an extraordinary span of the infrared spectrum, from just beyond visible light to wavelengths 28 times longer than visible red light. NIRSpec, the near-infrared spectrograph, has a capability that is particularly exciting for studying galaxy evolution. Its micro-shutter assembly allows it to observe up to 100 galaxies simultaneously in a single pointing. Each selected galaxy gets its own spectrum, revealing its redshift, star formation rate, chemical composition, and the presence of an active galactic nucleus. Before Webb, studying a large sample of distant galaxies spectroscopically was enormously time-consuming. Each galaxy had to be observed separately. With NIRSpec, hundreds of galaxies can be characterized in a single observation. This multiplexing capability transforms what is scientifically feasible. In a single pointing at a field of distant galaxies, NIRSpec can collect spectra that would have taken decades of Hubble time to accumulate. The result is a comprehensive view of galaxy populations at different cosmic epochs. How star formation rates have changed over time. How the chemical composition of galaxies has evolved. How the relationship between galaxies and their central black holes has developed over the history of the universe. The Webb telescope also carries a fine guidance sensor built by the Canadian Space Agency. This instrument serves a dual purpose. It keeps the telescope pointed precisely during long observations, measuring the positions of guide stars and feeding corrections to the attitude control system. And it can also perform its own scientific observations. imaging fields alongside the main instruments. Canada's contribution of the Fine Guidance Sensor was the basis for Canadian astronomers receiving 5% of the telescope's observing time. One of the most important things the Webb telescope does is look at things that are very old. Not old in the human sense, old in the cosmic sense. The universe is approximately 13.8 billion years old. The Big Bang occurred 13.8 billion years ago. In the first few 100 million years after the Big Bang, the universe was dark. There were no stars. There were no galaxies. The universe was filled with hydrogen and helium gas, slowly condensing under gravity into the first structures. Then, roughly 200 to 300 million years after the Big Bang, the first stars began to ignite. These first stars were very different from the stars we see today. They contained almost no heavy elements. They were made almost entirely of hydrogen and helium, the only elements that existed at the time. They were enormous, potentially hundreds of times the mass of our Sun. They burned intensely and briefly, producing the first heavy elements in their cores and then exploding as supernovae. These first stars ionized the surrounding hydrogen gas, ending the cosmic dark age, the epoch of reionization. Studying the epoch of reionization is one of the primary scientific goals of the James Webb Space Telescope. To see it directly, Webb looks for the most distant galaxies whose light left them more than 13 billion years ago. That light has been traveling ever since, stretching as it crosses the expanding universe, shifting from ultraviolet and visible wavelengths into infrared by the time it reaches our detectors. This is why an infrared telescope is needed. The oldest light in the universe has been redshifted into the infrared, and Webb is perfectly designed to catch it. The first stars of the universe, sometimes called population the third stars, have never been directly observed. They formed in a universe that contained only hydrogen and helium. They were very massive. They lived briefly and died violently, seeding the universe with the first heavy elements: carbon, oxygen, nitrogen, silicon, iron. Elements that did not exist before the first stars. Everything you are made of was forged in stars. The iron in your blood, the calcium in your bones, the oxygen filling your lungs. All of it came from stars that lived and died billions of years ago. The very first generation of stars created those elements from scratch, in a universe that contained none of them before. Finding direct evidence of population the third stars is one of the most ambitious goals in modern astrophysics. Webb may be able to detect extremely distant galaxies in which the dominant stellar populations are population the These galaxies would have very distinctive spectral signatures. No metals, intense ultraviolet emission from the hot massive stars, a chemical simplicity reflecting the first moments of cosmic star formation. The epoch of reionization is not directly visible to the eye in any image, but it is written in the spectra of the most distant objects. Before reionization, the universe was filled with neutral hydrogen that absorbed specific wavelengths of light. After reionization, that hydrogen was ionized and transparent. By studying the spectra of very distant quasars and galaxies, astronomers can measure at what redshift, and therefore at what cosmic time, the transition from opaque to transparent occurred. Webb is providing new and more precise measurements of this transition. Each new spectrum of a high redshift object adds a data point to the picture of how and when reionization happened. The first deep field image released by the James Webb Space Telescope in July 2022 was not just a scientific milestone. It was a moment. The image covered a patch of sky smaller than a grain of sand held at arm's length, and it was filled with thousands of galaxies, spirals and ellipticals and irregular smears of light at every orientation, some distorted by gravitational lensing into arcs and streaks, some so distant that their light had been traveling for more than 13 billion years before striking the Webb's mirror. NASA Administrator Bill Nelson described it as the deepest, sharpest infrared image of the distant universe ever produced, in a single pointing of the telescope, in less than 13 hours of exposure. An image that Hubble would have required weeks to accumulate. The image also contains something subtle and extraordinary that is easy to overlook. The brightest points in the image are not galaxies. They are stars in our own Milky Way galaxy. You can tell them from the galaxies by their diffraction spikes, sharp lines extending from each bright star in a characteristic pattern produced by the hexagonal shape of the Webb's primary mirror. 6 spikes, one pair from each of the 3 orientations of the hexagonal mirror segments. The stars with their spikes are in our own galaxy, nearby. Practically neighbors. The smudges and spirals and arcs behind them are other galaxies, billions of light years away. In one image, the nearby stars of our galaxy and the most distant galaxies in the observable universe appear together. The proximity of the familiar and the remoteness of the ancient held in one frame. The gravitational lensing visible in Webb's deep field images is not accidental. Astronomers specifically chose galaxy cluster fields for some of the deepest observations because the clusters act as natural telescopes. The mass of the cluster, hundreds of trillions of times the mass of the Sun, curves the space around it. Light from galaxies behind the cluster is bent and amplified. Distant galaxies appear brighter and larger than they would without the lensing, and sometimes they appear as multiple images, stretched into arcs around the cluster. Webb's sensitivity combined with gravitational lensing allows astronomers to study galaxies that would otherwise be completely invisible. Galaxies at redshifts of 10, 12, even higher. Galaxies from the first few 100 million years of cosmic history. Each arc in a Webb deep field image is a story. A distant galaxy, magnified and distorted by a foreground cluster, its ancient light bent around a mass of dark matter and hot gas, finally arriving at a gold mirror floating 1.5 million kilometers from Earth, to be counted and cataloged and understood. The deep field images from Webb are also being used for a scientific purpose beyond galaxy studies. By precisely measuring the positions of large numbers of galaxies, astronomers can map the distribution of dark matter in the universe. Dark matter is not visible, but it distorts the shapes of background galaxies through gravitational lensing. Statistical analysis of those distortions across large areas of sky reveals the distribution of dark matter. Webb's sharp images and sensitivity to distant galaxies make it a powerful instrument for this kind of weak lensing analysis. The James Webb Space Telescope can do something that no previous telescope could do with such sensitivity. It can study the atmospheres of planets orbiting other stars. When a planet passes in front of its host star, the starlight that filters through the planet's atmosphere carries the chemical fingerprints of that atmosphere. Different molecules absorb different wavelengths of light. Water vapor, carbon dioxide, methane, ozone. Each leaves a characteristic pattern of absorption in the spectrum of transmitted starlight. By comparing the spectrum of the star when the planet is in front of it to the spectrum when the planet is not in front of it, astronomers can isolate the contribution of the planet's atmosphere. This technique is called transmission spectroscopy, and the Webb telescope performs it with an accuracy and sensitivity that was essentially impossible before its launch. In its first year of operations, Webb detected carbon dioxide in the atmosphere of a hot gas giant planet called WSP-39b. This was not the first detection of carbon dioxide in an exoplanet atmosphere, but it was the most precise and detailed detection ever made. The data also showed hints of sulfur dioxide and several other molecules. Each detection is a step toward answering one of the oldest and most profound questions in science. Is the chemistry needed for life common in the universe? Does it appear naturally whenever the conditions are right? Or is it rare? Webb cannot answer this question on its own, but it is gathering the data that will inform the answer for the next generation of scientists. The precision of Webb's spectroscopic measurements of exoplanet atmospheres comes from a technique that is deceptively simple in concept, but extremely demanding in practice. As a planet transits its host star, the starlight dims slightly. The amount of dimming tells astronomers the size of the planet. But if the telescope is sensitive enough, it can also detect that different wavelengths of light dim by slightly different amounts. Molecules in the planet's atmosphere absorb specific wavelengths. Water absorbs certain near-infrared wavelengths. Carbon dioxide absorbs others. Methane has its own characteristic absorptions. By measuring the transit depth at many wavelengths simultaneously, Webb can build up an absorption spectrum of the planet's atmosphere. The signal is tiny. The planet's atmosphere represents only a thin annulus around the planet's disk. The fractional change in transit depth due to molecular absorption can be just a few parts per million. Webb's stability and sensitivity are what make this measurement possible. No vibration. No atmospheric turbulence. A cold, stable detector collecting photons with extraordinary precision. The result is spectra of planetary atmospheres at distances of hundreds of light years. The detection of carbon dioxide in the atmosphere of JWST 39b was achieved in a single transit. The planet passed in front of its star for a few hours. Webb collected the spectrum of the starlight filtered through the planet's atmosphere during that passage. The carbon dioxide signal was clear and unambiguous. Previous telescopes had required many transits to detect atmospheric molecules, and even then the detections were marginal. Webb detected carbon dioxide in its first attempt. This level of sensitivity transforms what is achievable in exoplanet atmospheric science in the years ahead. There is something worth thinking about in the loneliness of the Webb telescope's position. 1.5 million kilometers from Earth, beyond the Moon, which orbits at an average of 384,000 kilometers from Earth. Beyond any crewed mission ever flown, beyond any possibility of servicing or repair. The Hubble Space Telescope, by contrast, orbits Earth at just 570 kilometers altitude. Close enough that shuttle crews flew to it 5 times to replace cameras, install new instruments, and repair failing components. Hubble's longevity is partly a product of those servicing missions. Webb was designed to be beyond reach from the beginning. There was no plan for a servicing mission, no spacecraft capable of reaching L2 with astronauts. The telescope was designed to work perfectly without any human intervention. This was a choice that concentrated an enormous amount of pressure onto the launch and deployment sequence. Every mechanism had to work. Every mirror segment had to unfold correctly. Every instrument had to survive the journey and perform within specification. And yet the telescope was built and tested knowing that no repair was possible. That if something went wrong after launch, the billion-dollar mission would be lost. The pressure of that reality shaped every decision made during the telescope's construction. Every component was tested more rigorously than would have been necessary if repair were possible. The margin for error was zero, and the telescope performed. Every mechanism worked. Every mirror aligned. Every instrument cooled and activated correctly. The Webb sits at L2, fully functional, exceeding its design specifications, in the most challenging deployment any telescope has ever undergone. The decision to make Webb unserviceable was also influenced by the lessons of Hubble. Hubble's first mirror, famously, was polished to the wrong shape. A spherical aberration, a tiny error in the curvature of the mirror, made it produce blurry images. The error was eventually corrected by a servicing mission that installed corrective optics. But the embarrassment and cost of that repair shaped how subsequent large space telescopes were designed. For Webb, the approach was different. Rather than designing for serviceability and accepting the risk of error correction being needed, the engineers designed for perfection from the start. More testing, more redundancy, more careful quality control. The mirror was measured and remeasured. The mechanisms were tested and retested. And when Webb finally launched and performed perfectly, it validated that approach. Designing for unserviceability forced a level of engineering rigor that may have produced a more reliable telescope than a serviceable design would have. The constraint of no second chances turned out to be a feature, not just a limitation. The contrast between Webb and Hubble, in terms of servicing philosophy, also reflects how our relationship with space has changed. In the 1980s and 90s, the space shuttle was expected to make low Earth orbit routine. Servicing missions to Hubble seemed natural and achievable. By the time Webb was being designed, the space shuttle era was ending. No replacement crewed vehicle capable of reaching L2 existed or was planned. The assumption of serviceability that shaped Hubble's design simply did not apply to Webb, and so the engineers designed for perfection rather than repairability, a different philosophy, but one that appears so far to have worked. The Webb telescope has already changed how we see some of the most familiar objects in the sky. Its images of the Carina Nebula revealed star-forming regions of extraordinary detail, pillars of gas and dust, each one larger than our entire solar system, backlit by the radiation of young massive stars, individual protostars, stars in the very act of forming, visible for the first time in regions previously obscured by dust. Dust that is opaque to visible light but transparent to infrared. Hubble could not see through the dust. Webb sees through it as though it were not there. The image of the Stephens Quintet, a compact group of 5 galaxies, showed the gas dynamics between 4 galaxies that are interacting gravitationally in unprecedented detail. Shock waves where galaxies are colliding. Jets of material from an active galactic nucleus. Regions of intense star formation, triggered by the gravitational interaction between the galaxies. The Southern Ring Nebula, a planetary nebula surrounding a dying star, revealed 2 stars at its center for the first time, a hot white dwarf and a cooler companion, both embedded in an expanding shell of ionized gas. The cooler star was responsible for shaping the nebula's complex structure, something that was not known before Webb observed it. Each of these images represents not just a prettier picture than what came before. It represents new scientific knowledge, new understanding of processes that were previously inaccessible because the instruments available were not sensitive enough, or could not see through the dust, or could not resolve the relevant detail. Webb makes the previously inaccessible accessible. Webb's observations of star-forming regions have produced images that simultaneously answer old questions and raise new ones. The Carina Nebula image showed hundreds of previously unknown protostars, young stellar objects surrounded by their birth material, each one in the early stages of becoming a star. Some of these protostars are ejecting jets of material perpendicular to their accretion disks. The jets are visible in the Webb image as bright streaks extending from point sources. This phenomenon, called a Herbig-Haro object, was known before Webb. But Webb's resolution and sensitivity reveal it in regions where the dust was previously too thick to see through. Infrared light passes through dust that blocks visible light. Webb penetrates into the hearts of star-forming clouds that Hubble could only see the edges of. What is revealed is extraordinary. The interior of the cloud is filled with activity, stars forming at every stage of development, gas being ionized by the radiation of newly formed massive stars, pillars of dense material, sculpted by stellar winds, each one the cradle of future stars. A star-forming region is one of the most dynamic and violent environments in the galaxy. But photographed by Webb, It is also one of the most beautiful. The pillars of gas and dust in star-forming regions, like those in the Carina Nebula, are shaped by a process called photoevaporation. Intense ultraviolet radiation from nearby massive stars heats the surface of the pillars. Gas and dust evaporate from the surface and are carried away by the stellar wind. The pillars are being eroded, but they are also dense enough to partially shield their interiors from the radiation. Stars forming inside the pillars are sheltered for a time. Eventually, the pillar erodes completely. The stars inside, if they have formed successfully, are revealed. Webb's infrared vision can see the stars inside the pillars before they are revealed, peering through the dust to the forming stars within. The decision to place the Webb telescope at L2, rather than in a low Earth orbit like Hubble, was driven primarily by the need for the Sunshield. The Sunshield is the key to the telescope's ability to work at cryogenic temperatures, and the Sunshield only works if the Sun, the Earth, and the Moon are always on the same side of the telescope. At L1, 5 million kilometers in the anti-Sun direction, this geometry is maintained automatically. The Earth never passes between the telescope and the Sun from that vantage point. The Moon never passes between the telescope and the Sun. The Sun itself is always in approximately the same direction, always on the Sunshield side. But this geometry also has a consequence. The telescope cannot observe the inner solar system easily. It cannot study Venus or Mercury or the Sun directly. These objects are on the wrong side of the Sunshield. Observing them would require pointing the telescope toward the Sun, which is not permitted. The Webb telescope is therefore a telescope of the outer solar system and beyond, of distant planets, of nearby star systems, of the Milky Way, of distant galaxies, of the cosmic microwave background and the most ancient structures in the universe. It is optimized for depth and distance and age, for looking far away, for looking far back in time, for seeing things that no telescope before it has been able to see. The trade-off of losing inner solar system access for the ability to observe the infrared universe from a cryogenic platform is one that astronomers judge to be overwhelmingly worthwhile, and the results so far suggest they were right. Webb's inability to look at the inner solar system has not been a significant limitation for the science it was designed to do. Most of the great questions in modern astronomy lie outward, not inward. Galaxy formation, dark matter, dark energy, exoplanet atmospheres, stellar evolution, the cosmic web. All of these are studied by looking away from the Sun, not toward it. The one area where inner solar system access would have been scientifically valuable is the study of Venus. Venus has a thick, opaque atmosphere. Its surface cannot be seen in visible light, but it can be observed at specific infrared windows where the atmosphere is more transparent. Webb's MIRI instrument could in principle observe Venus at these wavelengths, but the telescope's thermal design prohibits pointing so close to the Sun. This is a real but minor scientific loss, more than compensated for by everything else the telescope can do. The designers and scientists who chose L2 over a more flexible orbit knew exactly what they were trading away, and they judged the trade overwhelmingly favorable. The science done from L2 by a cold infrared telescope exceeds by many times what could have been done from a warmer, more versatile position. As we come gently toward the end of our time with Webb tonight, let us think about what it means for this telescope to be where it is. 1.5 million kilometers from Earth, in the dark, in the cold, facing the universe. The Webb telescope does not know it is alone. It has no awareness of its isolation. It follows its programming. It points where commanded. It opens its shutters. It collects photons. It compresses and transmits data at a rate of about 28 gigabits per day back to the deep space network antennas on Earth. It performs its station-keeping burns when commanded. It keeps itself oriented with its solar panels toward the sun and its sunshield between itself and the light and heat of the inner solar system. And it waits, and it observes, and it discovers. But we know it is alone. We know what it took to get it there. The decades of planning, the billions of dollars, the thousands of people who contributed some part of themselves, some piece of expertise or labor or ingenuity to making it work. We know that it sits beyond any possibility of help, that it must work correctly or not at all. And we know that it is working. Right now, as you lie here and rest, the Webb telescope is pointed at some part of the sky. Its gold mirror is collecting photons that have been traveling for billions of years. Its detectors are converting those photons into numbers. Those numbers are being stored and compressed and prepared for transmission. And tomorrow, or the next day, some team of astronomers somewhere will download those numbers and begin the work of turning them into understanding. That is happening right now, in the dark. 1.5 million kilometers from where you are resting. The Webb telescope's primary mission lifetime is 10 years, defined by the amount of propellant carried for station-keeping maneuvers. But because the launch was so accurate, the telescope arrived at L2 using far less fuel than planned. The propellant reserve is now sufficient for more than 20 years of station-keeping. The limiting factor on the telescope's lifetime is therefore not likely to be fuel. It will be the degradation of components over time. The cryocooler for MIRI will eventually wear out. The detectors will accumulate radiation damage, reducing their sensitivity. The electrical components will age, but the telescope may continue to produce science well beyond its nominal 10-year mission. The hope among astronomers is that Webb will still be operating when its successor is being designed, that the two generations of telescopes will overlap, that scientists will be able to use Webb's deep survey data to plan observations with whatever comes next. Just as Hubble's legacy informed the design of Webb, Webb's discoveries will shape the science questions that the next great observatory is built to answer. As we drift slowly back now, from L2, back through the 1.5 million kilometers of empty space between the telescope and this planet, back toward the thin blue atmosphere, back toward the room where you are resting, let everything we have visited tonight settle softly into the quiet at the back of your mind. We began with a telescope floating alone in the dark, 1.5 million kilometers from home, at a point in space where gravity balances perfectly, where the sun and the earth and the moon all stay on one side, always, and the cold universe stretches out on the other. We learned about the Lagrange points, the 5 equilibrium positions in the Earth-Sun system that Joseph Louis Lagrange calculated in 1772. We learned why L2 is the ideal position for an infrared telescope that needs to stay cold. We followed the 29 days on the edge, the slow, nerve-wracking unfolding of the telescope in space, mechanism by mechanism, mirror segment by mirror segment. We sat with the gold beryllium mirror, 18 hexagonal segments aligned to nanometer precision, coated with less than 50 grams of gold spread across 6.5 meters of surface. We saw the first deep field images, thousands of galaxies in a patch of sky smaller than a grain of sand held at arm's length. We learned about transmission spectroscopy and the chemical fingerprints of distant atmospheres. We thought about the loneliness of L2, beyond servicing, beyond rescue, beyond any crewed mission ever flown. And we sat with the quiet, extraordinary fact that it is working. Right now, as you rest. Through all of it, one idea stayed close. We built something and sent it out into the dark, far beyond our reach. And it is watching the universe for us, gathering light from the beginning of time, sending it back, photon by photon, number by number, so that we might understand something true about where we came from and how vast the context is in which we find ourselves. There is nothing more you need to hold tonight. Let the web continue its quiet work. Let it collect its ancient photons. Let the gold mirror hold its cold vigil in the dark, and let yourself sink into the slow, unhurried passage of your own rest. The universe is vast tonight. The telescope is patient. And in this quiet room, 1.5 million kilometers from that gold mirror, you are exactly where you are meant to be. Resting. Still. Safe. If you are still with us, another quiet journey is waiting for you. And if this one helped carry you towards sleep, a like, a subscribe, or a gentle comment helps other tired minds find their way here too. From fall asleep, and from one tired mind to another across the soft, patient dark of tonight. Sleep well, rest gently, and good night.